Hello students, good morning to everyone. In this session, we will be finishing the complete chapter called Moving Charges and Magnetism. Right now, the topic of the particular session is conversion of galvanometer into ammeter and voltmeter. Conversion of galvanometer into ammeter and voltmeter. So before moving into the session, let us discuss about what exactly the galvanometer and ammeter, finally voltmeter. Then we will move into the topic. Let's see. Galvanometer. In the last class, we had completely discussed about a device called moving coil galvanometer. So that is this galvanometer. You know about working of this galvanometer. Now, let me remind you once again that this is the galvanometer. It's a highly sensitive instrument. Highly sensitive instrument. And what this sensitive instrument gives us? This is the sensitive instrument used to detect and measure small currents. What you can say, the small currents. So what I have written clearly, it is detecting and measuring the small amount of current. So generally the galvanometers will be made to measure a maximum of 1 milliampere current. 1 milliampere current. You might have seen the galvanometers in your physics laboratories. So they look like this. You can see there will be a scale inside these, and this is, for example, a 0 milliampere, and it will be 0.5 milliampere, and here it will be a 1 milliampere. So this scale will be like this. So maximum current this galvanometer can detect is how much? This is what you can see here. The needle is showing 1 milliampere. So the maximum current it is detecting this one. So this is the galvanometer is denoted with the symbol G. So what I can write, I suffix G, which is equal to the current through the galvanometer. Carefully see. Current through the galvanometer for the maximum deflection. For the maximum deflection. Remember, the maximum deflection for which current it takes place, I suffix G. When the current passing through the galvanometer less than I suffix G, so the needle will be deflected here or till here or till here. In that way it goes. But when the maximum deflection you need, maximum current must pass through this galvanometer. For example, if you pass 2 milliampere current through this galvanometer only, what happens? Imagine you have passed how much? 2 milliampere, but whereas its maximum deflection occurs at only 1 milliampere. But how much is the current we have sent into the galvanometer? 2 milliampere. What happens in that case? It cannot give the deflection of 2 milliampere. Because of what? Because its maximum range is only 1 milliampere. So what happens here? The maximum deflection of 1 milliampere it shows, and depends on the resistance of the galvanometer. It is measuring some current, means it is having a conducting wire. Every conducting wire will have some resistance. That's what we have discussed in current electricity chapter. So as there is a conducting wire present in this moving coil galvanometer, it will have definitely some resistance. According to the resistance, heating effects of electric current will be generated, because It's clearly written current I is flowing through that, and we know H is equal to I square RT. I hope you could recollect the heating effects of electric current. When more is the current, resistance is constant. When more is the current passing through that, heating effect will be generated, and there at a particular point the wire may burn. Understand, inside this galvanometer, when you send more amount of current through it, because the maximum deflection it could notice is 1 milliampere. For example, I am talking about, right? So some coil, moving coil galvanometer may be less than this or greater than this, whatever it may be. But generally, the galvanometers were made up of made to measure the maximum deflection for the current of 1 milliampere. For experimental purpose, I am telling you. Okay. So now, this is what I suffix G is current through the galvanometer for the maximum deflection. Now capital G is the resistance of the galvanometer. I am writing here. What's a capital G? Resistance of the galvanometer. It's a capital G, because it will have some resistance, I have told you. So remember these two things carefully. Right? This is about the galvanometer. Now, how we can be converting this galvanometer into ammeter and into voltmeter, we will be discussing now. Listen, before that, what is this ammeter? Let's come back to the ammeter concept. Ammeter. From the lower classes onward, you might be listening to the term ammeter, voltmeter. Even in current electricity also, we have discussed so many times related to the ammeter and voltmeter. So, ammeter is a device which could detect, ammeter is a device which can measure large currents. Which can measure what? Large currents. And before moving to the ammeter, come back to the galvanometer. I just wanted to add one more point to the galvanometer. And if you see the galvanometer definition, what I wrote here, not the description, what I wrote here, it will detect and measure the small amount of current. Here we have discussed about measuring only. In a meter bridge and potentiometer, I hope you remember the concept of meter bridge and potentiometer. We have used galvanometer. The purpose of detecting whether the current passing through that particular wire or not. That's it, right? So, this is the galvanometer is majorly used to detect the presence of the current in the circuit, right? So, major purpose of it is to detect. So, whether when we are detecting the current presence, definitely it could also measure the amount of current, but it is very small. Okay, now the resistance of this also must be very small, because when this wire will have, if the wire will have more resistance, the amount of current passing through that will be very, very less. Understand? Resistance is more, current passing through that will be very less. Understand? So that's the reason the resistance of the galvanometer will be very less, and this is used to detect the presence of the current in the circuit. Okay, now come back to the ammeter once again. So here ammeter is a device which can measure the large amount of current. Large amount of current. For example, if I want to measure some 100 milliamperes of current, the device I should use is ammeter. And this is the ammeter. For example, I have a resistance in an electric circuit. So, I wanted to find the current passing through this resistor. If I measure this current passing through the resistor by connecting an ammeter parallel to it, what happens? Ammeter also will have a small amount of resistance, right? So when this wire will have resistance, so definitely what happens? Definitely some amount of current from here. For example, I is the current I have forwarded here. So some amount of current will pass in this way also. So imagine it is I1, imagine it is I2. You understand? So some amount of current will pass through this ammeter. So only this current will be measured by this ammeter. So this current will not be measured by this ammeter. So but the aim of the ammeter is what? Amount of current passing through this resistor. So that's the reason this is the wrong connection. What is the correct connection here? If there is a resistance in the circuit, if you want to find how much is the current passing through this resistor, we need to connect the ammeter in series combination. So ammeter must be connected in series combination with the resistance in an electric circuit. Okay, clear? And one more important point here, ammeter must have a zero resistance, remember. So the ideal ammeter will have a zero resistance. Ideal ammeter must have. So ideal ammeter must have a zero resistance. When zero is the resistance, what happens? A maximum amount of current pass through that particular ammeter. Understand? When resistance of the ammeter is zero, maximum current pass through that, and our description about ammeter will be satisfied, because ammeter is used to measure the large amount of current. When it will have very less resistance, it could measure the large amount of current. Clear? This is about the ammeter. In which way we connect the ammeter in the circuit? So in which way? In series combination. Okay. Ideal ammeter will have zero resistance. Now let's move on to a voltmeter. So voltmeter is a device which measure the potential difference across any 2 points in the circuit. So that's what the voltmeter works. Right? That's what the purpose of the voltmeter in an electric circuit. Okay? It can measure the potential difference across any 2 points in the circuit. And this is the voltmeter must be connected in parallel to a resistor in a circuit. In parallel. How? If this is a resistor and the voltmeter must be connected here. Right? And then only potential difference between these 2 points can be measured by this voltmeter. And this voltmeter resistance must be infinity if it is ideal. Ideal voltmeter resistance must be infinity. If this resistance is infinity, then what happens? No current will pass through that. Our aim is not to find the current passing through voltmeter. If it is having high resistance, means infinite resistance, then complete current will be passing through here. Then we can find the potential difference between these 2 points. V is equal to IR. There is no point with the current passing through this voltmeter finding the potential difference across these 2 points. Understand? Clear? So what is the points we have to understand in the voltmeter? It is used to measure the potential difference across any 2 points in the circuit. And number 2, the voltmeter must be connected in parallel combination with a resistance in a circuit. And number 3, ideal voltmeter must be having infinite resistance. Okay, now we can move to the actual topic called conversion of galvanometer into ammeter and voltmeter. There is no separate ammeter and voltmeter around us. The galvanometer, which was moving coil galvanometer, we had discussed in the last class, right? The same moving coil galvanometer we will convert into ammeter and we will convert into a voltmeter, and let's understand that. Conversion of galvanometer into ammeter and voltmeter. I'd like to show you in a single board both the conversions. So first let's concentrate on ammeter. How we will be converting this galvanometer into ammeter. So I've just drawing a galvanometer whose resistance is capital G. To convert this galvanometer into ammeter, we need to connect a small resistance in parallel to this galvanometer. So that small resistance, I am writing it as S. So whereas that S is equal to shunt resistance. What is that S? Shunt resistance, which is having a very low value of resistance. That's called shunt. Okay. Now, this is the setup called ammeter. Now, it's so simple. When a shunt resistance is connected in parallel to the galvanometer, so this complete setup is called ammeter. How it is called ammeter, I just wanted to tell you. Listen. When there is only galvanometer, how much is the current you can measure? We can measure the maximum value of current passing through this is I suffix G. Yes or no? When there is only galvanometer. So now I wanted to measure a current I through this complete circuit. Total current through the ammeter, that is I. And when this point comes, this I will be divided into two currents. One current is I suffix G. I am imagining that out of this current I, the maximum value of the current for full deflection in this galvanometer is flowing. That's Ig. And remaining current is how much here? So this is I minus Ig. Through the shunt resistance, current passing through that is I minus Ig. Is it clear? Sure. Now, the total current I will be measured from this setup. That's called ammeter. Right? So, now lot of things we can derive from here for solving our numericals. So, what's that? Current I is total current that will be measured by ammeter. What is the ammeter here? So this complete setup is only called ammeter. Now, so what is Ig? So maximum deflection current through galvanometer. G, you know, resistance of the galvanometer. What is that? Resistance of galvanometer is G, and we had written S is the shunt resistance. So let us write here S is the shunt resistance. Is it clear? Now, from here, what is the potential difference across the galvanometer? So that's Ig into capital G. Definitely this potential difference is equal to potential difference across the shunt resistance because they are in the parallel combination. So that is equal to I minus Ig into S. Okay. So from here, what is the, see, this is one equation I have got. And another equation also. What is the net resistance of this ammeter? Net resistance, that is R effective of this combination will be R1, R2. R1 into R2 by R1 plus R2. That's a parallel combination finding effective resistance. So that will be G into S by G plus S. That is the net resistance of it. So I have told you, this is the shunt is having very low resistance. When the low resistance is again connected in parallel, the net resistance value will be what? Very less it becomes. So the concept of ammeter lies there. Ammeter should have the least resistance if it is an ideal ammeter. Ideal ammeter case is not possible, right, in reality. But in the case of ideal ammeter, the resistance must be zero. Very less. See, by connecting it in parallel, the complete resistance of the ammeter becomes very less here. Right? Now, again, come back from here. So, what is the shunt value here? Shunt value will be equal to Ig capital G divided by I minus Ig. Okay? Clear? So, one more point here. So, from here itself, S is equal to G divided by, so what I can write? I by Ig minus 1. Yes or no? You understand the point? S is equal to, what is the shunt resistance? G by I by Ig minus 1. So just this Ig comes to the denominator, it will be like that. You know, what is this I by Ig? So that's an important point. So that is called a sensitivity of this galvanometer, which is converted into ammeter. What is the sensitivity? Denoted with the symbol N. So that N is equal to I by Ig. What is I? I is the total current passing through the system, that's called ammeter, divided by current passing through this galvanometer. So these are the maximum equations which are useful for us while solving the numericals. That's it. So simple, right? What are the equations we have got? Number one is potential difference across this, potential difference across this is same. The first point, because they are connected in parallel combination. The two resistors are connected in parallel combination. And number two, what is that? Effective resistance of this circuit, G into S by G plus S. From this potential difference equal to this potential difference, we have got the shunt resistance. Most commonly asked questions are, what is the value of the shunt resistance to be connected? That's it. Okay. Clear? So let's move on to the voltmeter topic here. How this moving coil galvanometer will be connected, it will be converted into a voltmeter. Let's see. Voltmeter. The resistance, ideal voltmeter resistance must be infinite. So here what we need to do, the resistance of the complete setup must increase, right? How we can increase the resistance of the setup? So this is the galvanometer G here, and there is a resistance R, right? So here S is the shunt resistance, here R is the high resistance. R is what? High resistance. So when high resistance is connected in series with the galvanometer, so then this complete setup is called as a voltmeter. That's it. So when the galvanometer is only used, it is just measuring the small amount of current as well as small amount of potential difference, because V is equal to IR. When I is very small, what happens? So potential across that also will be very small. The same thing here. So when this galvanometer is connected to the shunt, and it becomes ammeter. When this galvanometer is connected to high resistance in series, what happens? Here total resistance will increase. What is the total resistance value here? G plus R. Understand? So R effective in this case is how much? G plus R. The net resistance is increased. Then current passing through the circuit will decrease. You got the point? Clear? So then potential difference across these 2 points can be found easily. Even higher values also this system, this kind of setup can measure. Okay. So now let's talk about the current. You know, current passing through this galvanometer is I suffix G for the maximum deflection. That is what we are assuming, right? Sometimes we send the current, less current than this Ig, so that the deflection in the galvanometer will not be maximum. That's it. Okay. But our assumption is for maximum deflection, what is the current required? That is what we are sending. Now, let's see the potential difference across this is how much? I suffix G plus potential difference across this is how much? Because as they are in series combination, same amount of current only flows. I suffix G into R. The potential difference across this plus the potential difference across this is equal to what? Is equal to potential difference across the setup. Understand? Which we are going to measure, right? Which we are going to measure. Voltmeter is a device which will measure the potential difference across any 2 points in the circuit. Okay. Now here what we can write. What is the high resistance need to be connected to make the galvanometer into voltmeter? That is this R, right? So I can write from here Ig into R, which is equal to V minus Ig into capital G. Okay. So from here R is equal to V minus Ig into capital G divided by Ig. So R is equal to V by Ig minus capital G. So this is how the numericals also you can solve by using this kind of simple formulas. There is no much formulas are needed here. It's so simple. Potential difference across this plus potential difference across this is equal to total potential difference of the circuit. That is what the voltmeter do here. Okay, so this is the simple concept. Now let's solve the numericals also based on this conversion of galvanometer into ammeter and voltmeter. Let's solve the first question. A galvanometer of 100 ohm resistance. So what is given here? Capital G is 100 ohm. A current of 10 raised to minus 3 pass through the galvanometer. So means I suffix G is given as 10 raised to minus 3 ampere. How can it be converted into ammeter of range 10 ampere and voltmeter of range 10 volt? So ammeter of range 10 ampere, voltmeter of range 10 volt, right? Sometimes it will be given like ammeter of range 1 to 10 ampere, means you should consider maximum value only, because current passing to the galvanometer we have considered maximum. Okay, here also sometimes the question can be given voltmeter of range 1 to 10 volt. We need to consider the maximum value to solve the numerical, right? Listen to me once again. Galvanometer resistance is given. A current passing through the galvanometer is also given. How can it be converted into ammeter and how can it be converted into voltmeter? So first thing, how can it be converted into ammeter? By connecting this galvanometer and a shunt resistance parallel to it. Definitely the setup is converted. The setup, that means from the galvanometer, this setup is called as ammeter. Okay. So by connecting this shunt, this in parallel, we say this is converted into ammeter. So we know this I current is passing through the ammeter, which is how much is given? 10 ampere. Okay. So I suffix G will be passing through galvanometer and through the shunt it will be I minus Ig. Alright. So the concept is to find shunt. So we know Ig into capital G is I minus Ig into shunt. And shunt resistance is equal to, what is that? Ig into capital G divided by I minus Ig. Okay. So let's find out, let's substitute everything. What is Ig here? 10 raised to minus 3 into G. What is the galvanometer resistance is given? 100 divided by I minus Ig. What is the total current passing through the ammeter? So this is 10 ampere. It's 10 minus Ig. What is Ig? It's 10 raised to minus 3. You can solve like this. S is equal to, this is 100 divided by, what is the numerator I am talking about? 1000. Right? So this is numerator divided by, what is the denominator here? 10 minus, so this is 1 by 1000. Okay, this is denominator. So here it will be 2 zeros, 1 by 10 divided by, here it will be 10,000 into, 1000 into 10. It's 10,000 minus 1 divided by 1000. Okay. Now, so what is this? 1 by 10 divided by, it's 9,999. Okay, see this one, 10,000 minus 1 divided by 1000. Okay, so your S value is 1 by 10 into 1000 divided by 9999. Okay, see, this will go to the numerator, that became reciprocal here. 1 0 0 cancel here. What is your answer here? 100 by now 9999. Oh, right? See, this is the shunt. So, if you find this, the value will become very small. Right? You get in 0.000. So that means the shunt value need to be very small. Do not get confused by getting the small value, because the concept of shunt is like that. a low resistance must need to be connected in parallel to the galvanometer. Okay, so like this numericals will be asked. Let's see this. How the same kind of galvanometer, when maximum deflecting current is Ig is passing through it, how to convert it into the voltmeter? We know the same galvanometer need to connect to the high resistance. So the question is, what is that high resistance need to connect so that this voltmeter of range, this need to be measured? We know this current Ig is passing through both high resistance and our galvanometer. Ig into G plus Ig into R is equal to V. What is our aim? R, right? So how we will convert the galvanometer into voltmeter? By connecting that high resistance. What is that high resistance? That's a question. So Ig into R is equal to V minus Ig into G. So R is equal to V minus Ig into G by Ig into R. Okay. So now let's substitute what is V. V is 10 minus Ig. It's 10 minus 3 into G. G is 100 divided by Ig. 10 to the power minus 3 into sorry here. So that's a R, right? It's only Ig here. Understand? So this R is equal to V minus Ig into G by just this Ig goes to the denominator. That's it. Right? So here 10 minus 100 divided by 1000 divided by 1 by 1000. Okay. Now R is equal to, so this will be 1000 into 10. It is 10,000 R. Easy way you can solve this is 2 zeros cancel here. This is 10 is the LCM, the numerator I am talking about. 10 into 10, it's 100 minus 1. This is numerator. Denominator will be 1 by 1000. And this is 99 by 10 into, so that this denominator goes to the numerator, it will be 1000 divided by 1. 0 gets cancelled. The answer is 9900. This is volt. Understand? Sorry, 99 ohm, 9900 ohm. Because this is the resistance. We have converted the galvanometer into voltmeter, but by connecting this much high resistance, see, whereas shunt resistance is very, very small, where here our high resistance is 9900 ohm is connected, so that this galvanometer is converted into voltmeter of range 10 volt. Clear? So in that way numericals will be asked. Let's solve some more numericals related to that. Let's solve some more numericals. What is the value of shunt which passes 10% of main current through the galvanometer of 99 ohm resistance? So simple. What is the value of shunt? Shunt, immediately by seeing that, you should try to make a simple diagram of how the galvanometer converted into ammeter. This is G and there is a shunt here. Current I passes through that. This is Ig and current passing through this shunt is I minus Ig. And from here you could write Ig into capital G is equal to I minus Ig into S, right? Let's see what is the value of the shunt which passes 10% of the main current through the galvanometer. So by keeping this shunt, what happened? This Ig, current passing through the galvanometer, is 10% of the total current. So that means I suffix G is equal to 10 by 100. 10% of what? Total current. Understand? I suffix G is how much? 10% of the total current. Let's substitute this 10% of the total current into this one. And they have clearly mentioned that the G value, the galvanometer resistance is, 99 ohm. The galvanometer resistance they mentioned, it's 99 ohm. Let's take this, right? Let's take this one. So what is this? From here, Ig into G plus this Ig into S, which is equal to I into S. Our aim is to find shunt. That's the reason I am writing. So this Ig into G plus S, which is equal to I into S. So this shunt I can write it as Ig by I into G plus S, right? So what is this shunt value? Ig by I, it's clearly mentioned. Ig by I is 10 by 100, clear. Ig, this I comes here, 10 by 100 into G plus S. So what is our G? It's 99 plus S. Okay, so this is 0, 0 gets cancelled. And cross multiplication, if you do, it will be 10 into S, which is equal to 99 plus S. So 10S minus S, it's 9S, which is equal to 99. So 9 11s. So S is equal to how much? 11 ohm. Right? So when we keep 11 ohm resistance here, how much current is passing through the galvanometer? Just 10% of the main current is passing through that. That means 90% of the current passing through this shunt resistance only. Okay, so this is how the numericals will be asked. Now let's see the last problem of the session and the chapter. A maximum current of 0.5 milliampere can be passing through the galvanometer. So Ig is equal to 0.5 milliampere is passing through galvanometer. Galvanometer is having resistance of 20 ohm. Calculate the resistance to be connected in series. So that is high resistance. Because which resistance we are connecting in series with the galvanometer? Shunt resistance or high resistance? So definitely high resistance. In practical experience, you have this high resistance will be in the range of 1000 ohm, right? 10,000 ohm, 5,000 ohm, in that range it will be. To convert it into a voltmeter, yes, that's what we discussed. This is high resistance of range 0 to 5 ohm volt. That means V is 5 volt. Immediately you should recollect the diagram. So this is a galvanometer and this is the high resistance. And what we can write here, I suffix G, capital G, plus I suffix G, capital R is equal to V. Right? Our aim is to find this R. Okay. So let's write this I suffix G into capital G plus R, which is equal to V. Right? So let's write everything. I suffix G. How much I suffix G? 0.5 into 10 raised to minus 3 into G. What is the resistance of this galvanometer? 20 plus R, which is equal to V. V is 5. Okay. So this I can write 20 plus R, which is equal to 5 divided by the 0.5 into 10 to the power minus 3 will come here, right? 0.5 into 10 to the power minus 3. And this 20 plus R is equal to 5 into this 10 raised to minus 3 goes to the numerator. So that will become 10 raised to 3 divided by 0.5 means 1 by 2. Understand? Again, look at this interesting thing. So 20 plus R is equal to 5 into 10 raised to 3 into this 1 by 2 goes to the numerator, that will be 2. Right? So now 20 plus R is equal to 10 to the power 4 because 5 into 2 is 10. 10 into 10 raised to 3 is 10 raised to 4. So now what I can write, R is equal to 10 raised to 4. 1, 2, 3, 4. That's 10,000. Minus this plus 20 comes here, it will be minus 20. This R is equal to how much? 10,000 minus 20, it will be 9,980 ohm. Got the point? Clear? So this is how numericals related to the conversion of the galvanometer into a voltmeter will be asked. Okay, so soon we will be starting the another chapter. I hope you understand the chapter here. There are more sign conventions are involved in this chapter, and carefully go through the sign related to the magnetic field, etc. Okay, so thank you so much. All the very best.